Okay, thank you so much, Mr. Nikhil. This is Abdurahman Grada. Hi, everyone. This is Abdurahman Grada, reservoir engineer. And actually, I'm glad to share with you some thoughts about special core analysis on the platform of petroleum associating engineering. Before I start, I'd like to say that if you don't have the background of reservoir engineering, you might find this webinar a bit of challenging to understand. But don't worry, I will start with a very simple theory, and step by step we will dive deep into the rock, and we will end up with we will have a solid background on special core analysis after this presentation. So let's start. First things first, starting with the introduction of the special core analysis and its main applications in oil industry. And then we will start talking about relative permeability analysis. We will know how to measure the relative permeability, the techniques to measure the relative permeability, and how can we check the consistency of relative permeability curves, and how to refine the data to be used in simulation modeling. After that, I will be talking about the capillary pressure, including the main features of PC curves, and how can we average different PC curves using different techniques for averaging capillary pressure, according to the rock types and rock properties. And finally, the last and not the least, I'll be talking about the wettability. And we will see what is wettability and what's its effect on production profile and water flooding projects. So let's start. Special core analysis is the essence of the evaluation and management of hydrocarbon reservoirs. And high quality and reliable data will allow us to maximize the performance of the reservoir, by understanding different aspects. For example, here we have the capillary pressure. The capillary pressure, where we can build the saturation height models for the hydrocarbon in place determinations, and also to find out the best correlation for the pore throat size distribution. And it's quite interesting that the capillary pressure curves provide means to estimate the fluid distribution versus depth, independently from logs. It's quite independent, and it's quite independent approach from logs. So if you have uncertainties in the logs, it's a really good tool to help us determine the fluid distributions versus depth. And then we have the relative permeability data, which is widely recognized for the prediction of oil recovery during the displacement by water. And of course, if you have reliable relative permeability data set, can reduce the uncertainty of the dynamic reservoir modeling and provide a sound foundation for the reservoir engineering studies. And the last but not the least is the wettability, which affects the amount of oil that can be produced at the pore level. And wettability also affects the water flood performance and determines how easily water can be injected and how it moves through the formation. So let's start with what's the concept of relative permeability. In petroleum reservoirs, only a small fraction of the original oil in place is economically recovered by either primary, secondary, and even tertiary recovery. And a considerable amount of hydrocarbon ends up unrecovered or trapped in the porous media, which results in oil recovery factor typically less than 50%. And this is for the optimistic case to have 50%. And the water flooding is by the most widely used method to increase the oil recovery. And the oil that remains in the porous media after water flooding is called the remaining oil saturation, which is way larger than the relative permeability residual oil saturations. So that's why determining the relative permeability characteristics of the reservoir is a key parameter for the reserve assessment and for the recovery estimates. Actually, the main application of the relative permeability is to control the advancement and the mobility of different fluids simultaneously coexist in the porous media, and therefore controlling the recovery of the fluids. But however, deriving the reliable relative permeability data set, it might be like a major challenge. And like in reservoir engineering, this challenge has been present like for many decades and might be so on for the near future as well. So let's see how can we talk about the relative permeability. The permeability that we measure in routine core analysis, we call it absolute permeability. And there is only one fluid inside the rock, so it's more like a rock properties. So what if we have more than one fluid in the rock? I mean, there's no, not only water or gas in our system. For example, we have oil, water, and gas coexist together. So in this case, a new term shows up, which is the effective permeability. So what is effective permeability? As you can see here, it can be defined as the ability of the porous media to conduct the fluid where its saturation is less than 100% of the pore space. And then, so if we have like more than one fluid, so now we are talking about effective permeability. It's not about absolute permeability. And now what is the relative permeability? The relative permeability, which is like the ratio of the effective permeability of a given phase, let's say oil, to the absolute permeability, of course, in the presence of the other fluids. So now we have the absolute permeability, the relative permeability, and the effective permeability. And this is an example that you can see here of relative permeability chart of drainage process, where the I can see where the pores are primary filled with water, and well, this is actually where the pores are primarily filled with water, and the oil migrates and displacing water. So here we have the water relative permeability decreasing as the water saturation decreasing, and the oil water is not I mean, the oil will not be able to move until it reaches a certain saturation. And above that saturation, the oil will have enough capillary pressure to displace the water, and therefore the relative oil permeability increases. And in the following slides, we will see more about the features of the relative permeability. So now we know what is the general concept of the relative permeability. Let's answer the question which says, what are the methods of measuring relative permeability? So once we, as a reservoir engineer, we receive data, I think it's wise to know the methods and how they measure the data, so we can have an idea about the conditions of the measurement and what's the best method and why we use this method and not. Okay, so relative permeability can be generated from different sources, such as mathematical models and experimental models. However, experimental methods are more desirable for many reasons. For example, they produce specific relative permeability relationships for a specific reservoir. And also, it's currently the best available approach to resemble the flooding process, performed in a representative core samples. So our discussion today will be restricted to the relative permeability data that are derived from the lab experiments. In fact, there are a number of techniques have been developed for deriving the relative permeability, are described in literature for many years ago, and generally there are three methods exist to measure the relative permeability. As you can see here, we have steady state and unsteady state, and finally the centrifuge. In the steady state method, the relative permeability is measured directly. However, in the unsteady state and the centrifuge, the relative permeability is indirectly measured. And there are a couple of difference and pros and cons for each one. For example, the steady state method has an advantage of like a simple calculations but the disadvantage of like a long procedures. However, in unsteady state takes less time and requires more complicated calculations. And for the centrifuge, for example, the method is fairly quicker than the rest. I mean, it's really fast, but gives, you know, the relative permeability of displaced phase only. It cannot give you like oil relative permeability and water relative permeability at the same time. It gives you only one, as we will see in a minute. So starting with the steady state, you know, the steady state experiment, we start with 100% of water saturations, and then we inject the two phases at the same time, you know, both non-wetting and the wetting phases at different flow rates. And the flow rate, you know, of one phase is increased while the other is decreased gradually. And, you know, at each rate change, the pressure drop and the saturation are, you know, closely monitored. So we monitor the pressure and we monitor the saturations. And once we reach the equilibrium, or what we call it the steady state condition within the system, once the pressure drop across the core and the saturations are not changing with the time, so at that time, the effective and relative permeabilities for individual phases are actually can be computed using Darcy's law, because we have the pressure drop and we have the flow rates, we have the length, the cross-sectional area of the core and the viscosity of the fluid. So we can have the calculations of relative and effective permeabilities directly. In this method, the relative permeability curves can be determined over a representative range of saturations, which is like basically the most advantage of this method. In addition to that, somehow it's like simple calculations required to accomplish this method. However, it's worth to mention that capillary pressure forces are usually ignored, and also the experiment is time consuming, therefore it's going to be really expensive. And if you notice that it's not actually a displacement process, so it does not necessarily simulate the reservoir fluid. I mean, we're not actually representing, I mean, real representation. There's no real representation of the reservoir fluid displacement mechanism where one fluid displaces the other. That's how it goes in our reservoirs. I mean, other words, that there is an uncertainty in the fluid distributions using this method. Moving to the second method, which is the unsteady state. In unsteady state method, only one of the phases is injected into the core to displace the other. I mean, the idea is to monitor the pressure differential across the core and to monitor the production history, where we control the multi-phase displacement process, and then to back calculate the relative permeability values using one of the analytical methods. And in this method, actually, we don't inject two fluids, we inject only one fluid, and we don't have to wait until stabilization, but we use a technique called Buckley lever in order to calculate the relative permeability. So we start with 100% of water saturation, and then we inject oil until we reach the irreducible water saturation. So we measure the effective oil permeability at this saturation, at the irreducible water saturation. And after that, we start our water injection, just, you know, simulating the water flooding process where the water saturation increases and the oil saturation decreases until like there's no oil coming out of the cell, which means we reach the residual oil saturation. And then we measure the effective water permeability at residual oil saturation. So we did the two measurements, the oil relative permeability at irreducible water saturation and the oil relative permeability and the water relative permeability at residual oil saturations. I mean, the relative permeability at the end points. Basically, there are different ways have been developed to determine the relative permeability data from unsteady state displacement. However, this approach like neglect the capillary pressure effects as well. The method is actually preferred to steady state for its rapidness. I mean, it's much faster than the steady state. And to some extent, it can be, depict the reservoir fluid displacement mechanism, where we have one fluid displaces the other. But the main disadvantage of this method is to the boundary effect, especially at low rates, where the theory of Buckley lever is not actually valid in is not valid like in tight formations. So that's why this is the main limitations of the unsteady state. And moreover, it's kind of complex interpretations. It's not the calculations of unsteady state is much complicated than the steady state. So moving now to the third method to measure the relative permeability, which is the centrifuge. Here we have the centrifuge or relative permeability test. Essentially, the method is based on the concept of rotating a core at various angular velocities, to initiate the force, drainage, or imbibition process. So this is the first thing. We initiate the force. For every rotational speed, the fluid production is collected to the pipette and measured at equilibrium. And the average saturation is derived from, the effluent production volume. The model interprets the centrifuge experiment as the gravity drainage, process. And there are several assumptions that, the centrifuge assumes. That it actually assumes that the capillary effects are negligible, and the invading fluid mobility is much larger than the displaced fluid mobility. And another assumption, actually, it says that the acceleration along the samples is uniform. So these are the main assumptions of this method. And there are several types of centrifuge experiments. For example, there is a single speed and multi-speed, and there is a constant flow rate centrifuge techniques, and there are so many techniques that inside the centrifuge method. A major advantage of the test is what like the large pressure differentials can be created across the core block without creating an unstable displacement. And this high pressure difference, results in relative permeability data over an extended saturation range. So we can have good data even at the lower oil saturations values. The main limitations are actually values of water relative permeabilities cannot be defined from a single speed displacement of oil by water. It can only gives you the oil relative permeability, because the test can either gives you the oil relative permeability or water relative permeability, because there is a displacement process and the output is only one curve. Another thing that if you have illite in your clay, you may end up with fines migrations, which plugs the pores and the pore throats, and this might affect your permeability and reduces the general permeability in your system. So these are the main limitations for the centrifuge. So now maybe some of you are confused that like which technique is the best technique that we can use in our calculations in our work. Actually, the choice of measuring techniques, for relative permeability can be a really challenging task. For example, each one of the previously mentioned techniques is claimed to yield the residual oil saturations, and the relative permeability, they gives you both the relative permeability and the residual oil saturation. However, ignoring some physical aspects may result in unreliable results. So let's see what are the best choice for each experiment. So each experiment has got an advantages. So now let's focus on the advantages for each one. Now let's summarize them actually. Centrifuge experiments are often used in studies where the gravity drainage is identified as the dominant recovery mechanism. And unsteady state method is more often used, because of its rapidness and it's really fast test. In some cases, the steady state method is needed to fully define the curve ranges. So at the end of the day, integration the results from different types of tests can be the great help of recognizing which parts of each data, are reliable and which parts are invalid. Okay. For unsteady state, the test provides reliable results with the mid-saturation range, and the experiment is not valid at high and low saturation range. So now I know where to take the data, where the data are more reliable in unsteady state, where it's in the mid saturations ranges. I mean, in the curvature, not in the endpoints, but in the middle of saturations. However, the centrifuge results can be used as a supplementary of unsteady state in the low and high range. So for me, this is the technique that I usually take. I use centrifuge and unsteady state. I combine them together, and for the moderate mid-saturation range, I take it from unsteady state, and for the at low and high ranges, I give more weight to the centrifuge method. So these are basically, in very, briefly talking about the methods that measuring relative permeabilities. Let's move on to the main characteristics of relative permeabilities. As the water saturation is increased in the core, there are the two curves are defined. Actually, there is an oil relative permeability and water relative permeability. As you can see here, this is the KRO and this is the KRW. For homogeneous blocks, the curves are smooth and monotonic. And as you can see here in the chart, that the oil relative permeability, the dashed lines, is decreasing and the water relative permeability is increasing. And the final oil saturation at the end of the test, is referred to be as a residual oil saturation, or name it as SOR, where the oil, will not be produced. And then we have the water relative permeability at SOR, which is referred to that water relative permeability endpoints, which is here is about like 50, let's say 7 or 0.57, more or less. This is the value often used as an indication of the wettability of the rock. The water relative permeability. In many cases, the residual oil saturation is too high due to many reasons. For example, due to the premature ending of the flood, and therefore the water relative permeability will be too low. So that's why we need to refine the results, as we will see in the following slides. Then we have the irreducible water saturation, which above this saturation, or connate water saturations, above this saturations, where the water starts to move, and basically the saturations decides the time for the breakthrough. And another important characteristic of the result is the saturation at which value KRW and KRO are equal, where the saturation at which they cross. And actually this is this value can be used to compare between curves. If they cross a chord before 50%, it could be something, and if they cross a chord after 50%, it could be another thing, as we will see when we will talk about the wettability. So this is the main characteristics. We have the oil relative permeability and water relative permeability, residual oil, and the irreducible water saturation. Here we have the water oil relative permeability consistency check. Actually, this can be applied to the crude relative permeability to make sure that our data are valid to be used for further use for like simulation modeling. So the first thing that we do actually to check the consistency, that there should be agreement between the oil relative permeability values for unsteady state water flood method and the centrifuge oil relative permeability test. They should be in agreement and somehow they should be close to each other. And in the case if they don't agree, I would give more weighting for the water flood method over the especially for the intermediate water saturations, as I've said before. And another thing, I will check, the values of residual oil saturation at the end of the various tests, of course, assuming that they have, the same rock type, they should be ordered as following. So the highest residual oil saturation, it should be by the test of, reservoir conditioned water flood or unsteady state reservoir conditioned water flood. And then we have the centrifuge oil relative permeability test, and the lowest SOR, it should be given by the centrifuge PEC test or capillary pressure test. So the SOR by these tests can tell us about the consistency of the test. If the order is not, the same, that somehow tells us that there is a kind of problem in the consistency in our data. Then we have the water relative permeability at the endpoint value of unsteady state water flood should be less than the water relative permeability endpoint measured by the centrifuge test. So we compare these two values together and we make sure that the one which was measured by water flood or unsteady state is less than the one which measured by centrifuge test. Another quality check that I usually do is the resultant relative permeability curve from unsteady state water flood when plotted to a logarithmic scale should concave downward, and when plotted to a linear scale, it should be like concave upward. And if it wasn't the case, actually that could be due to either one of two things. I can see here these data are somehow valid because in linear scales moves upward and downward concave in the logarithmic scale. But if the case is not this one, so actually it could be due to invalid values for water relative permeability at low water saturations, actually due to the lack of capillary equilibrium at the start of the water flooding. And also it could be due to excessive flattening of the curve at high water saturations, maybe due to blogging of mobile finds. So this is like gives you a hint of if your water relative permeability are valid or not. Another thing which is used to check the consistency is the Cory exponents. We call it oil exponent and water exponent. NO and NW, they usually determine from the final curves should be consistent with wettability measurements. And here is the table that made by Style in 2013, links between the exponents and water relative endpoints with the wettability type. So if you have like strongly water wet, the oil exponent, it should be ranges from 2 to 3, and NW somehow from 4 to 6, and the same thing for water relative permeability endpoint. And next slide, I will show you how to estimate, the oil exponent and the water exponents. Then we have the end value. If the end value is approaching or exceeding 1, so that's maybe the result of the wettability of the core having been altered to oil wet by, inappropriate coring fluid. For example, if it was using the oil-based mud, so that's might changing the wettability and end up with endpoint values exceeding or even approaching 1. Another thing that I use as a quality check is the very high water relative permeability in point can also be the result of actually not desaturating samples adequately before flooding. So the samples are not actually desaturated properly. So that's why you have high water relative permeability in your system. So these are the techniques I use to make sure before I start analyzing and before I start putting this relative permeability set in any further use, for example, in simulation modeling. And this is here, this is a raw data, as a real data of a relative permeability. And now, as you can see here, we have the water saturation and we have oil and water relative permeability. So let's do the analysis for this real data. The first step, actually, we plot the oil relative permeability and water relative permeability versus water saturation, in both linear and logarithmic scale. And of course, the curves should be concave upward in the linear scale and downward in the logarithmic scale. And the second step, we estimate what we call true residual oil saturation by normalizing the oil saturation range using different assumed values for true residual oil saturation by this equation. Okay, so we assume different values for residual oil saturation and then noting which value produces the line that is approximately straight line on the plot of log oil relative permeability versus log of normalized oil saturation. This value provides an estimate of true residual oil saturation. So now we have the true residual oil saturation. In the following steps, we estimate the water relative permeability in points by extrapolating the trend of the log of water relative permeability versus log normalized water saturation to the point equivalent to the true residual oil saturation, where the SWN equals to 1. So we have the water relative permeability in point. And the step number 4, we estimate the NO and NW actually for the individual points by determining the slopes of the lines constructed from oil relative permeability at reducible water saturation or water relative permeability at residual oil saturations. And then we take the straight line and we measure it for this is for the NO and this is for the NW. And in the final step, we display the results of oil relative permeability and water relative permeability using these equations and like the parameters that we defined previously, and the raw data are refined properly. So these are my refinement to the data, and we took in considerations all the corrections that we have to make for each method. So that was like briefly about the relative permeability. We knew what are the methods used to the relative permeability and which method are, what are the advantages and disadvantages for each method. And then we know how to do the refinement for our data using, very simple techniques of just style. So now let's talk about the capillary pressure. Actually, understanding the capillary pressure behavior is quite important to optimize the reservoir characterization and the hydrocarbon production. And it's one of the most important factors that determines the distribution of hydrocarbons in the reservoir. And it's used to define the distribution of the connate water saturations above the free water level, where the free water level could be estimated from RFT or repeated formation tester. So in a reservoir at initial conditions at equilibrium exists between bouncy forces, and capillary forces. These forces determine the initial distribution fluids, and therefore, of course, determines the volume of the fluid in place. And a well-known example of capillary bouncy equilibrium is the experiment, which, like a number of glass tubes actually of varying diameters are placed into a tray of water, and the water level rises up in the tubes and reaching its highest point in the narrowest of the tubes. And the capillary tubes of different diameters can be linked to different sizes of pore throats in our pore system in the reservoir. So the capillary effect is actually apparent whenever two immiscible fluids are in contact, and it's actually a result of interaction of attractive forces between molecules in the two liquids. So if there are two immiscible fluids in contact, there will be like what we call the surface tension that will raise as a result of unequal attraction between the molecules of the same fluid and the adjacent fluid. And obviously, there will be more attraction for the same fluids, and this surface tension will create a pressure differential between these two liquids. And the pressure difference between, it sounds like really complicated, isn't it? And the pressure difference between the water phase and the oil phase is called the capillary pressure. So once there are two immiscible fluids are in contact, there will be, because of attractive forces of the molecules, there will be a pressure difference between these two phases, and this difference in the between these two phases, call it the capillary pressure. So the capillary pressure is the difference between non-wetting phase and the wetting phase, and can be estimated by this equation, which is like function of interfacial tension, and also function of the radius of the capillary tube, and also function of the contact angle. Here we have the typical capillary pressure curve, where we plot the capillary pressure versus the water saturation. At first, we have the entry pressure. Okay, so what is the entry pressure? Entry pressure is the minimum pressure at which the non-wetting fluid begins to enter the highest pores in your rock sample, and it's often referred as a threshold pressure. The lower the permeability and pore size of the rock, so the higher pressure will be required to do the displacement. I mean, this is for constant wettability. Now I have a question, like why the pressure is high? Simply because of like high pressure is required for a non-wetting phase to enter and penetrate a small radii and displace the wetting phase. This is in the case if we have small pores. So let's take an example of if the pores diameters are very uniform in size. So very little additional pressure would be required to desaturate the water, and the plot of the pressure versus saturation would be very flat, as it's the case here. This is the plateau period. So we are the oil displaces the water as the water saturation decreases, but that doesn't require additional pressure. Doesn't require additional pressure to do the displacement. Why is that? Because of uniform in size. I mean, they are all the same. They are uniform in size, and you have a good quality of your reservoir. And so that's would be like very flat. So there is like what I said as like a plateau on the curve until we reach the irreducible water saturation, which is the water cannot be displaced. So if the sample have, this is the opposite example, where the sample is very heterogeneous pore size. So the capillary pressure curve will exhibit a more gradual transition to the irreducible water saturation. So the saturation zone, if it's like flat, that means we have a good permeability and large pore system, pore throat sizes, and fairly uniform. And if we don't have like a very steep relative PC curve, that may indicate of like a bad quality of the rock. And now I can see, okay, this one. So this is an example of different PC curves. Okay, so starting this one, which the best PC curve? I mean, which PC curve has got the best rock properties and the highest permeability and the highest pore size? I think the sample is named as 154. This sample has got the highest permeability because it was really flat and the irreducible water saturation was really low. So that it was flat until we reached it to irreducible water saturation, and even the irreducible water saturation occurred at low saturation. However, in this one, actually the entry pressure was relatively high, and the transition zone was almost steep, and there is no flat period, and the irreducible water saturation occurred at a very high saturation. So this is tells you that's a very tight formation. However, this is not only a tight, but also a heterogeneous reservoir. Okay, because as the oil displaces water, the pressure, it requires more pressure to do the displacement until it reaches to the point that no matter how much pressure you do, the water will not be produced. Okay, so now let's see what are the factors that affecting the capillary pressure. Now we've talked about the pore size and distribution, and let's summarize this in 4 points. Okay, so as I said earlier, that pore size and the distribution of the pore size present in the rock actually will probably the strongest influences in the capillary pressure behavior. And you know, in this example, there are 3 different systems. We have chalk and we have sandstone with high and low permeabilities. The key features of pores, actually in most chalks that are very similar, but the pore throat size are very narrow, but they are similar sizes. So that's why the entry pressure will be very high, since a significant non-wetting phase pressure is required to enter the largest pore throat. As you can see here, the entry pressure was really high, but once the non-wetting phase enters the pores, a very little additional pressure is required to desaturate the pores until it reaches irreducible water saturation. So that's why we have the plateau is very flat. And then we have another example of sandstone, which is high permeability and low permeability. And you can see here the effect of permeability on this PC curve. This is have got higher permeability, so it was really flat until it reaches irreducible water saturation. So it was flat and has had less value of reducible water saturation. And this one, the permeability was low, so that's represents the steepness and the slope in the transition zone. So this is the first example. Then we have the interfacial tension. Actually, for the interfacial tension for a given contact angle and the pore radius, the value of PC will increase if the interfacial tension increases. So they are proportional. Maybe the photo here is not really clear, but this one has got the highest interfacial tension and this one has got the lowest interfacial tension. Then before that, we have the density, the fluid density. Actually, it has an impact on capillary pressure if the density difference between water and the hydrocarbon phases is small. We have a small difference in density, so the capillary pressure will be small. And if you have like high density, because there will be high interfacial tension and will be high capillary pressure. And for the wettability, actually the capillary pressure will be less in oil wet than water wet system. And here I have a question for you. Why we have less PC curve in oil wet than water wet system? The next topic, I'll be talking about the wettability. So I would like to hear your answers after I explain, the wettability. So as you can see here, this is the angles, and the water wet has a very low angle, which is 0. Strongly water wet has a 0 angle, and this is the angles that have high angles. That means water wet, oil wet. So this starts from water wet to oil wet, and as you can see here, the capillary pressure goes from water wet to the oil wet. So while we have this capillary pressure in oil wet, we have less capillary pressure than water wet. I will tell you by the end of this webinar. And of course, before that, I'd love to hear your thoughts. Okay, the same thing. This is the methods that are used to measuring the capillary pressure. There are 3 main capillary test methods: the mercury injection, and the centrifuge method, and porous plate. So starting with the mercury injection method. Actually, in mercury injection method, a cleaned and dried sample is placed in a mercury air system, and after evacuation with air, the sample is injected with mercury at stepwise pressure increments. And the volume of the mercury injected at each pressure step is measured, until the maximum pressure is reached, which is usually, let's say, 2000 psi. And this is typically takes from 20 to 30 pressure steps are used to define the drainage curve. In this experiment, mercury is the non-wetting phase, and the air is assumed to be the wetting phase. And before we start this experiment, we should have the helium porosity available to calculate the mercury. There are some automated equipments possible to reach a very high pressure, about 60,000 psi. So the porosity can be measured, because the mercury will definitely fill all the pores, since it reaches like a very super high pressure. And any remaining air is compressed. That air, so that air that is in the porous plate method, or the mercury injection method, will never reach an irreducible value. So this is a particular problem in a low permeability rocks, and it must be addressed in the data interpretation. And this is the main disadvantage of the mercury injection. Moving on to the following one is in centrifuge method. The test actually is saturated in brine, and actually placed in a core hole specially designed for the operation in a centrifuge. And the sample is then spun at series of increasing rotational speeds. And as a result of the centrifugal force, the brine is expelled and replaced by air, or it might be replaced by oil, depends on the type of the test. And at a set of speed, the brine will be produced from like the sample until equilibrium between centrifuge and capillary force is reached. So the produced brine is collected on a tube. So we have different saturations and different pressures. So this is the main idea of the centrifuge method. And then finally, we have the porous plate method. And the third method, actually, the porous plate method is also known as the restored state technique. The samples are initially saturated with brine and desaturated with air or oil at stepwise pressures. It's the same idea. And the saturation pressure curve often shows that a sudden change so that the reducible water saturation, might be much higher than the true value. Okay, so despite these problems, air brine pores plate tests are the method of preference for so many special core analysis parameters. For me, if you ask me like which method I use, I would say that I use pores plate and centrifuge method actually to estimate the connate water saturation, but I don't use mercury injection because mercury injection is not recommended to use to define the water saturation or connate water saturation, where it's like two fluids, the mercury and air, are non-wetting fluids. However, I use mercury injection to define the best correlation for the pore throat size distributions estimations. So these are the main methods for the used to measure the capillary pressure. And this is a case study of how to analyze our data and how to make our data. Actually, I just wanted to bring a real data to how to analyze data, because some people, they know a lot about capillary pressure and they know a lot about relative permeability, but when it comes, when you give them a real data and you say, okay, just could you please analyze it, and they just stuck and they don't know how to do the calculation. So that's why I thought about bringing the real data and how what are the procedures. They are very simple procedures actually we do to analyze the thing. So let's this is like a case study, and the step number one actually. There is a systematic method usually used to analyzing the primary drainage capillary pressure data, which is based on Brooks and Cory correlations, which was back in, I think, in 1964 or something. And the first step to conduct the visual inspection of the plotted results to see if the curves are smooth and concave upward when PC is plotted on either linear or logarithmic scales. This is the first step. And the second step is to estimate the irreducible water saturation by normalizing the saturation range using different assumed values for reducible water saturation, and plotting the log PC and log normalized water saturations, and noting for which the assumed value gives a line that is approximately straight line, and in doing this, it may be necessary to disregard data from either early or the late values in the test, where the SW may be too high due to inadequate drainage time. So that's why we only take part of this one and we disregard these values. And the step number 3, we determine the values for entry pressure and lambda. The capillary entry pressure is estimated by extending the straight line constructed through the trend of reducible water saturations when it's like normalized water saturation equals to 1, where we have the entry pressure of 0.1, and the slope for the straight line through the data at lower water saturations. So that defines the pore size distribution index, lambda, or the curvature of your PC model. And then in step number 4, the values of capillary pressures can now be calculated from SW equals to 1 to the value nearest to the end of the lab test, using capillary pressure curve characteristics discussed in in the previous steps, and using this equation for PC, now we have the entry pressure, and we have the normalized water saturations, and we have the lambda. We can create our refined capillary pressure. And in step number 5, when PC data actually are scaled to the same fluid system, differences between curves are usually related to differences in the porosity and rock type. I mean, difference in porosity and permeability. Okay, so there are different techniques actually used for PC normalizations, and the most widely used is the J-levered functions. The J-levered functions normalize the PC data with respect to the rock quality, porosity and permeability. So the PC with a similar rock quality will have a similar PC curves to end up with one PC curve for each rock type. For example, we had various PC curves, but these ones have similar PC curves, and they could be grouped to one PC because they share the same rock types. However, these rock types seems to be tight formation, and they have different rock types from this one, so we cannot have one PC for all these types. It depends on your rock quality and the if it's homogeneous or heterogeneity. So that's why PC averaging technique is really useful to recognize the PC curves that has the same rock type or not. So that was the main thoughts about the capillary pressure. We knew how to measure capillary pressure, and we knew how to understand the capillary pressure curve, if it's like good property or bad property, and then we know how to do the refinement of Brooks and Cory method of your PC curve. And now we go to actually for me is the most important method, the most important aspects in the reservoir, which is the wettability assessment. So what is the concept of wettability? Maybe some of you wondering why I put wettability in the last, because like many of authors, they put the wettability at the very beginning, because wettability contributes in relative permeability and also contributes in capillary pressure. But for me, I wanted to put the wettability at the end of this presentation, because once you understand the concept of both relative and PC approaches, so now you can have an idea about what is the effect of wettability on these two things. Okay, so with multiple phases flowing in the reservoir, understanding the wettability becomes really important. So let's define what is the wettability. Actually, wettability describes the relationship between the contact of two fluids and a solid. So this is the system. We should have two fluids and two immiscible fluids and solids. And when I say like the rock is a water wet, that means the preference of a solid to be in contact with water rather than another fluid. And the type of contact is characterized by the contact angle, between the fluid and between the fluids and the solid. So if the contact angle measured through a liquid is less than 90 degrees, so the system is said to be water wet. And if the angle is more than 90 degrees, it's more an oil wet. So as you can see here, the difference in contact angles for the water wet system and oil wet reservoir rock surfaces. So to simplify the thing, actually there are either water wet and oil wet. But in a homogeneous porous material, saturated oil and saturated with oil and water, the solid could prefer to contact with oil or water to be either strongly water wet or strongly oil wet. However, in reality, our reservoir rocks are really complex structures and often comprising a variety of mineral types. And each mineral have like different wettability, making the wetting character of the composite rock really difficult to describe. So that's lead us to the case where the solid does not prefer one fluid to another, which is like a condition is termed as an intermediate wetting or neutral wetting. many experts today, I mean, they believe that most oil reservoirs have some mixed wetting characteristics, and the original water wet condition is changed by the oil migration. I mean, this is the default in most of the cases. So now the question is, why we analyze the wettability? In fact, wettability controls the productivity and controls the oil recovery and the original wettability of a formation and the altered wettability during and even after the hydrocarbon migration, affects the profile of the initial water saturation, and the affects the production characteristics in the formation. So it's really important characteristic, and it's really important concept to understand. It has been said that most reservoirs are water wet before oil migration. So let's start with the water wet system, along the transition zone, where the saturation changes gradually from mostly oil with irreducible water at the top, and at the top of the transition zone, and the water at the bottom. As you can see here, we have oil plus irreducible water saturation, and this is only a water at the bottom of the transition zone. And this distribution, so this is for the water wet system. Actually, this distribution is determined by the pressure difference between oil and water, which we call the capillary pressure, as as explained before. And I think the answer of my question is somewhere here. And in the case of the oil wet system, the oil migrating into an oil wet reservoir will display a different saturation profile. Essentially, there will have only oil at the top, and we will have water plus a residual oil saturation at the bottom of the transition zone. As you can see here, the capillary pressure required for the oil to displace water until we reach the irreducible water saturation is less in oil wet. Okay, and this is actually was my question. Why the the capillary pressure is less in oil wet? Actually, because of here we have irreducible water saturation, and so this is the oil will require a higher pressure to displace that to displace that water which is trapped in the tight formations. That's why the pressure is increasing. However, here I mean, it's oil wet and it's saturated by oil, so there is no difference in there's no interfacial tension. Interfacial tension is 0, so that's why it's really flat and until it reaches to reducible water saturation. Sometimes because of the lithology variations, we have different wetting states. For example, in the tight zone, may remain water wetting if the oil could not migrate to that space. I mean, they are basically water wet, and they became water wet because the oil could not reach to that pore space. Okay, because it required a high capillary pressure, and that pressure was not available for the non-wetting phase, while the surrounding formation are converted to a more oil wet states. So this, for example, there are several carbonate reservoirs in the Middle East are thought to have the variation in the wettability by layer, and actually the cause of this phenomena is not yet understood. So sometimes we might have oil wet and water wet at the same reservoir, depends on your lithology. But actually, I don't think that it's as simple as this. There might be different characteristics involved in our saturation. So let's see what is the effect of wettability on water flooding. I mean, most of the fields now are producing thanks to water flooding. It's really important to know what is the effect of wettability on water flooding. Here we have starting with the water-wet system. In the water-wet system, the water will be like in a small spaces, as you can see here. These small spaces are occupied by water, and these spaces, were not invaded by oil, and the oil will be in the large pores. And in the water flooding process, both phases are flowing, and the oil relative permeability, which is KRO, is high since the oil flow since the oil flows through the largest pores, and decreases as the oil saturation decreases. And the opposite for the water relative permeability starts very low and increases as the water saturation increases. So the water saturation increases preferentially in the smaller pore space first. At first, it starts to fill the smallest pore space due to the wetting forces. And as the displacement moves from the smaller to larger pores, the water increasingly occupies pore throats, the larger pore throats that were formerly, filled with oil. So now the small pores, we have only water, and in the larger pores, we have water plus the pre-existed or plus oil. Okay, so if the pressure of water is higher than the entry pressure, so the water will displace oil. Otherwise, the oil will be trapped and will not be produced. And this is actually the trapped oil could be the target of enhanced oil recovery. So now we can say that wettability has an effect on water flooding performance, because imbibition forces determine how easily water can be injected and how it moves through the water wet formation. And based on simulation studies, actually that water breakthrough occurs later in water flooding, and more oil is being produced before the water breakthrough in a water wet system. I mean, in the water wet system, the breakthrough occurs very late, and the more oil is being produced before the water breakthrough. But in oil wet reservoir is the opposite, where we have early water breakthrough, and we have at the same time less oil is being produced before we reach the oil breakthrough. So this is basically the main effect of wettability on water flooding. Then actually I have a very interesting concept, which what makes the wettability change. I mean, wettability alteration is a really critical topic. And for example, the oil composition is a key to changing the wettability of naturally water wet surface. Why? Because of some compounds that change the wettability. We call them as like a polar compounds, such as asphaltene, and it depends on the solubility of these polar compounds. For example, if the crude oil have like low solubility, so the asphaltene, will have high tendency to change the wettability. I mean, in other words, if you have asphaltene in your composition, it's a good indication of wettability change. I mean, it's most likely to be a mixed wettability. If not an oil wet, at least it's a mixed wettability. I mean, it cannot be a strongly water wet. Another thing is the injected fluid. I mean, the injected fluid might alter the wettability in a water flooding project. This action may result in improved or sometimes damage the injectivity or the productivity of your well. Because the uninjected, once you inject the brine, which dissolves the solid content, or sometimes because of different pressure and different temperature, this will lead to pH differs from those of the formation brine between the fluid, injected fluid and the formation brine. This can induce the wetting change as well. So the injected fluids may inject your wettability, and in many times may reduce or damage your reservoir system. And for the temperature, actually, for example, the quartz tends to be more oil wet at higher temperature. But for calcite, there tends to be more water wet at higher temperature. Then we have the pressure history. This one is really critical in wettability alteration, because as the reservoir is produced, the pressure depletion can alter the composition of your crude oil, which can lead to asphaltene depositions, in the reservoir, or you might have, because of reduction in the gas, you might have gas condensate or formation of the gas cap. All these may affect in wettability distribution in your formations. So all these factors are actually may change your wettability in your reservoir. Well, we came to the last part of this webinar, which is the methods that are used to measure the wettability. There are two main methods: Ammott-Hervey method. This method used actually for takes into account 4 basic measurements. As you can see here, there are amount of oil that is spontaneously and forcibly imbibed, and the amount of brine water that is spontaneously and forcibly imbibed. And the displacement of both like spontaneous and the total volumes are measured for both oil and water, and the ratio of spontaneously displaced. The ratio of the spontaneously displaced to the total displaced volume is calculated for both oil and brine phases. And the Ammott-Hervey wettability index at the end, we have wettability index is calculated by subtracting the displacement by oil ratio from the displacement by water ratio, using by subtracting these ratios, we end up with an index of Ammott index ranges from +1, which is strongly water wet, and -1 means strongly oil wet. And if it's close to 0, that is like mixed wettability or intermediate wettability. And the last method, or the second method, is the USBM test. A centrifuge spins the core sample at stepwise increasing the speeds, and the sample starts at irreducible water saturations in a water-filled tube. And after periods, like at several spins rates, the sample reaches the residual oil saturations, and it is placed into an oil-filled tube for another series of measurements to change. And the same idea, actually, we have an index from +1 for strongly water wet and -1 to strongly oil wet. And the best exercise is to combine both methods and integrate with relative methods. They combine these two methods and integrated with relative permeability and capillary pressure, so you make sure that the consistency of your results are valid. Thank you so much for your attention. It was a bit of complicated topic, because we were talking about a microscopic scale. So actually, it's not easy to understand, especially if you have if you don't have the background of reservoir engineering. But anyway, thank you so much for your time, and yeah, I'm glad to hear your thoughts. Thank you. Nikhil, are you here? Well, it sounds Nikhil is not there. Let's see the comments.